Welcome back to our unit on probability, and thank you for subscribing to my YouTube channel. Be sure to hit that like button when you're done watching if you like the episode. Today I'm asking you to complete exercises 41 through 46, and I would tell you right away, this first exercise, similar to exercise 41, it's based on, these problems, they're based on a little something we're going to call counting principle. Now, all right, so here's the story with this. You're basically sending a message of just binary digits, just a 0 or a 1. That's all the message is. Now, because of various disturbances, probability is that 1/10 of a time the message gets kind of flipped like this. Or if it gets flipped like this, not desirable. We'd like it to go, if we're communicating a 1, we want it to be a 1. Communicating a 0, we really want it to be a 0. But that only happens 90% of the time, or 9/10 of the time. So in an effort to try to make sure we get our message through, we transmit the exact same number 3 times in a row. That is a triple 0 instead of 0, and triple 1s instead of 1s, as you see down here. Maybe I should highlight those. Yeah. All right. So this is going to, what this is going to be an exercise in is something we're going to call majority decoding. So with that, it says, we're going to transmit 0, 0, 0. What could happen, of course, is that the digits are all correct, and maybe one of them fails, like in these. Maybe 2 of them fail, like in these examples, or maybe they all fail. So the idea here is we're going to check the probability of that. We're going to see what's our probability of success, where success is going to be defined as those. These are going to be failures. So that's going to be my set of messages that are coded correctly. Let's see for correct. So here's the story. To get the 0, 0, 0 like this, you know what? I'm going to change my color. To get the 0, 0, 0, that would happen when I take 9/10 times 9/10 times 9/10, 0.9 times 0.9 times 0.9. That will come out to like 0.729. And okay, but wait, there's more. What we also need to look at here are these 3 sequences. Now, the 3 sequences like this, the 0 is coming through twice. If it happens any of these 3, the 0 comes through twice and the 1 comes through once. Order won't necessarily matter right off, but we'll take 0.9 times 0.9 times 0.1, but because that's 3 different outcomes I just described there, I'll multiply that times 3. So as we can see on this particular problem, we get 0.972. This tells us that 97.2% of the time, if you're writing it as a percent, that's our success rate. 97.2% of the time I have success. No words on the consequences of the other 2.8% of the time. All right, a similar problem to exercise 42. You have some binary spinner where it's just 2 possible outcomes, just the letter A, letter B. So we spin it 6 times. Let's say maybe one of our outcomes is ABB, ABB. Okay, that'd be one possible way of happening that. Now the probability of coming up with exactly ABB, ABB, where we're saying the order matters, 1/3 times 2/3 times 2/3 times 1/3 times 2/3 times 2/3. Sure, because the 1/3 belong to the A, so there's those. Understand? So okay, so we have that, and we can calculate this. Probably that one particular outcome is simply 16 out of 729. Now, of course, be careful, because that's just one specific instance of getting 2 A's and 2 B's. That's why this sentence is here. It must not be thought of that this alone is the probability for 2 A's and 4 B's, because there's actually quite a number of ways I could get 2 A's and 4 B's. So we're going to learn about a simple counting method in this next section here. But I would tell you that even without that special counting method, I would invite you to consider that if I viewed it as having 6 different blanks to fill in, and on those 6 blanks, kids, if I know that I have an A here, and there's only one more A to go, how many more can there be? How many different places can the A be? Well, it could be here, or 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 it could be here. That's 5 different places it could be. So that's 5 ways, plus, but wait a second. what if, let me change my color again. What if the first A happened here? So it's like B, A. Now there's 1, 2, 3, 4 ways I could set down the second A. If this was a B and my first A didn't happen until here, there's 3 ways I could set, 3 places I could set down the second and final A. You see where we're going with this? It's going to be 5 plus 4 plus 3 plus 2 plus 1 on the end. So this totals up to 15. Boys and girls, what this means here is that I'm going to take that probability of that one particular outcome I had up here, the 16 over 729. I'm going to multiply 15 times 16 over 729. And on this particular problem, on the similar problem, which was exercise 42, I said, you're asked to provide the best approximation to 3 decimal places. If I did that on this problem, it's 0.329. As you can see, the old text would say, oh, it's approximately 1/3. No. Give a 3-digit decimal representation as you go to do exercise 42, please. This next one here, it's another probability type question where Abel, he's living at point A on the diagram, not well labeled. That's okay, I'll put it in there right there. There's my point A. Here's point B. We'll call this C. Actually, excuse me, C's already labeled. Let's call this D, please. There we go. And there's E. We'll call this point F. Why? Because I can. So, he lives at A. This is Abel. And he has 5 friends, each of whom lives 4 blocks away. Friend B, friend D, friend C, friend F, friend E. Okay. So then, if he's going to see friend C, if he just goes randomly, whether it's north or east, so to start, he can either go north or he can either go east. That is to say, well, hold on. So he can go this way or he can go that way. This will be north, this will be east, you understand. So, what I have here then, let's get this out of the way. We can see, we could actually just sit here and count this, right? Say it goes north, north, east, east. That's going to be one way to get there, north, north, east, east. But maybe he went north, east, northeast. North, east, north, east, like so. Or maybe he goes north, east, east, north. It's getting messy in here. Whatever. There we go. All right, there we go. Let me erase these and make some new lines. But what if he goes east first? If he goes east, north, north, east. Oops, I didn't mean to draw a diagonal line there. There we go. Or maybe he went east, north, or he goes east, east, north, north. So as you can see, east, east, north, north. Okay, we got that one. And east, north, northeast, and east, north, east, north. All right. So now, of course, the probability, he's flipping a coin to choose these paths. Probability along each path is just going to be 1/2 that he goes that way. If he's making 4 such trips, this will be the probability of any particular one. It's got to be 1/2 to the power of 4, which is 1/16. But there is a grand total of 6 of these. 1, 2, 3, 4, 5, and 6. So we'll take 6 times 1/16, and we can see that that is pretty obviously going to be 3/8. See? So there's our answer right down here. All right, so I want you to complete up through exercise 46 today. Read the intro to the next section, please, up through 47. Thank you for watching my video. Be sure to subscribe and to be good for your parents. Have a great rest of your day, and I will see you soon. Bye.